A fusion plasma is one of the most complex objects humans have ever tried to hold. It burns at 100 million degrees, it reshapes itself in thousandths of a second, and you can never touch it directly or put a probe in its core. So how do you fly a machine you cannot see inside? You build a second machine. In software, we call it a digital twin. It is a living mathematical model of the Hyperion breeder that runs in step with the real machine. Physics and data locked together. The equations know how plasmas ought to behave. The sensors tell us how this plasma actually behaves. The twin's entire job is to hold those two stories in agreement, moment to moment. The architecture is a pipeline, and it is worth walking through. Sensors feed raw measurements in. The twin estimates the true state of the plasma. Physics models carry that state forward in time, and the result becomes a prediction the control system can act on. Sense, estimate, model, predict, control, a loop that closes many times every second. Each stage feeds the next, and the quality of the whole is set by the weakest link in that chain. Start with the hardest part, knowing the plasma's full state. We have only a handful of instruments looking in from the edge, and we need temperature, density, current, and magnetic shape everywhere inside. State estimation is the discipline of reconstructing that whole interior from a few partial indirect views. The twin does it with a predict and update cycle, a Kalman filter, in its extended and unscented forms because a plasma is deeply nonlinear. It predicts where the plasma is heading, compares that against the newest measurements, and corrects. Each pass tightens the estimate, and it carries an honest error bar the whole way. So the controller always knows not just the answer, but how much to trust it. At the center of that reconstruction is a live equilibrium solve. The twin solves the Grad-Shafronov equation in real time to find the nested magnetic surfaces that give the plasma its shape. This is the same calculation that offline codes take minutes to grind through, now done inside a control budget measured in milliseconds. The twin can also run in reverse. From its internal state, it generates synthetic diagnostics, virtual sensor signals, and checks them against the real instruments. When the virtual and the real agree, we trust the state. When they drift apart, we learn exactly where the model is still weak, and that disagreement becomes a to-do list for improving the physics. A twin that can grade itself is a twin you can actually rely on. Not every question needs the same level of detail. The twin runs at dialed fidelity, a fast reduced model when milliseconds are scarce, a full physics model when accuracy matters more than speed. Choosing the right level for the right moment is itself part of the engineering. A control loop and a design study ask very different things of the same twin, and it must serve both. Here is what makes all of it worth the effort. The twin forecasts 50 to 100 milliseconds ahead, a solid trace of the present, a dashed forecast of what comes next, and a band showing the lead time we have won. In plasma control, a tenth of a second of warning is the difference between a gentle correction and an emergency shutdown. And all of it lives under a hard clock. Real-time means the twin must finish its work inside a fixed millisecond budget, every single cycle with no exceptions. A brilliant prediction that arrives late is simply worthless. So let us be exact about who does what. The twin and its machine learning models advise. A deterministic rules engine decides. Inside hard physics limits, normalized beta at or below 5, and Q95 at or above 5. The intelligence proposes, the fixed rules dispose. And let us be just as exact about status. This twin is validated in open simulation today. It is a conceptual design, not yet an operating machine. Its calibration against real hardware begins at our first gate, G1, when twin output meets real data for the first time. And we publish the entire method openly, which points to the deepest use of all. Before a single coil is wound, the twin lets us test the machine inside the machine, trying operating points, shaping the plasma, finding the failure long before it ever reaches hardware. It is a wind tunnel for a plasma, running long before there's any plasma to fly. Every reactor we build twice, once in software, then once in steel. The software one comes first, and it never stops learning.